Okay, so in the last class we are carrying out the derivation of affine projection algorithm. So this was a page. We had a generalized version, a generalized function which is a function of all the weights w0, w1 up to w capital N minus 1, and also lambda is a vector, it is a function of lambdas also, lambda 0, lambda 1 up to lambda p, because there are p plus 1 constraints. Okay. So each constraint has one Lagrange multiplier, and this was the thing. All these were derived last time, so I will not be wasting time in redoing this or restating this. Okay. This is a function, we have to derive it with respect to each lambda k, and we have to differentiate it with respect to each w. Okay. If I take any partial derivative of this with respect to lambda k figures here. Okay. So actually it will be this, you can see x transpose n dw. Okay. So only this and lambda transpose. So this lambda 0 dot 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 lambda k dot 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 lambda p and this thing. So lambda k will multiply this x transpose n minus k vector. So, it is like this x transpose n w. So, row vector into w column vector minus d n, this is scalar, that will be multiplied by lambda 0, but there is no lambda k there. Lambda k will multiply this term x transpose n minus k, this row times w. Okay. There is a filter output at n minus kth time index with a filter coefficient vector w. So, this output minus d n minus k. All right, this is the thing. This will be multiplied by lambda k. So, when you take a partial derivative with respect to lambda k, only this will result, and that is what we had obtained earlier. Okay. And you equate that to 0, so you get this. So, by these partial derivatives with respect to lambdas, I get this. All right, this equation. So, this will be satisfied. So, therefore, because whatever be the w n, whatever is the w, that must satisfy those p constraints. By forming this generalized function and introducing the Lagrange multiplier, we see when you differentiate this L with respect to lambda case, those conditions get satisfied, right. That is, if you want to find out minima of this function, you have to take minima with respect to both lambdas and w's. So, here it shows that minima will automatically satisfy those constraints. These are the constraint equations, okay, for k equal to 0, k equal to 1 up to k equal to p. So, those will be satisfied. Now, comes the other derivative. Here w minus, now L is if you take this w minus w n norm square, we have seen in the context of LMS, this is minus, the two cross terms are same. So, twice w transpose w n plus norms, I mean you can write either way, either in terms of norm or just this. W transpose w is norm square of w. Similarly, w transpose n w n is norm square of w n. I am writing like this, you could write as norm square also. So, this is the part, and then you have got that extra part, right. So, therefore, if I take this derivative, this function w transpose w, we have already seen in the context of n LMS algorithm. What is w transpose w? The w 0 square plus w 1 square plus dot dot w k square plus dot dot like that. Any partial derivative with respect to w k will be twice w k. So, if you put all the partial derivatives in a stack, twice w 0, twice w 1, twice w 2 dot dot, there is 2, if you take common, it is 2 w. So, this term will give rise to 2 w. Here twice w transpose w n, that means w 0, w 0 n, w 1, w 1 n, dot 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 dot. So, if you differentiate with respect to any particular weight, say w k, so it will be this twice the term is twice wkn. So wk goes because of differentiation, it will be twice wkn. So if you now stack them, these derivatives, so twice w0n, twice w1n, twice w2n, dot dot dot, which will be twice wn. This has no w, so after differentiation it goes. Here lambda transpose x transpose w minus lambda transpose dn. Lambda transpose dn has no w, so that will go away because of derivation. Lambda transpose x transpose n w, it is nothing but x n lambda transpose w, because you know from basic matrix theory, any matrix, if you have A into B transpose, is B transpose A transpose. Lambda may be a vector, but it is also a matrix, isn't it? P plus 1 cross 1. So x n lambda transpose, which is lambda transpose x transpose n. Okay, so that times w. So if you call it, if you give it any name, say maybe alpha. So alpha transpose w. And now if you differentiate it with respect to each component of w and put those results in a stack, you will get nothing but alpha vector, like we get wn vector here. All right, alpha vector. W transpose, I am sorry, I wrote wrongly here. No, it is okay, this is fine, this is fine. This term I am talking of twice w transpose wn, and that is same as twice w transpose n w, twice w transpose n w. So w transpose n w when differentiated with respect to w gave wn. Instead of wn I have alpha, so alpha transpose w when differentiated with respect to w, put in a stack all the derivatives, it will be alpha, like it was wn there. So it will give rise to alpha. Alpha is this, which means this derivative will be lambda transpose, sorry, alpha is x n lambda. So it will be x n lambda. Now remember, it is a vector equation, not a scalar equation. X n is a matrix, lambda is a vector, lambda 0, lambda 1 up to lambda p, and this is also a gradient vector. All right. This is the situation. This I have to equate to 0 vector for minimization, for minima. All right. That means if I take this to the right hand side, what I have is twice is x n lambda, lambda vector. Okay. Now, so if I multiply, pre-multiply both sides by x transpose n, that is twice, 2 remains same, so 2 is just kept in the front, then x transpose n times this vector, here also x transpose n, x n lambda. All right. Now this matrix will, if this matrix is invertible, x transpose n x n, it is a square matrix, Hermitian matrix. Actually, I will talk in detail about this. So if this is invertible, your lambda will be just, you know, inverse of this will come here, twice inverse of this, then x transpose n, then this. All right. Okay. So let me go to the next page. Let us study this matrix x transpose n x n. What was our x n? It had a vector x n vector, then x n minus 1 vector dot 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 x n minus how many? P. Xn was the filter input data vector at nth clock. So, it was x of n its size is n cross 1. So, this matrix is n cross p plus 1. Okay. If the columns are linearly independent, that is, there is no linear relation between them, that is, you cannot write any column as a linear combination of the others, okay, then we say it is full rank, full column rank. Okay. In that case, x transpose n, x n will be invertible. How? We are coming to that. Consider this matrix x transpose n x n. So, this is Hermitian. Okay. Obviously, if you call it A transpose is again, if you take the transpose of it, you get x transpose n, this will get transpose come here and x transpose n will come here after transpose. So, transpose cancels. Okay. So, A is A transpose, Hermitian. Not only that, it is positive semi-definite always. Why? Because if you take for any vector C not 0, C non-zero, C transpose A C, it will be, we can see that it will be non-negative. Why? Because C transpose, you replace A by x transpose n, x n C. X n into C, it is a matrix times a column vector, you call it D. So, D is a column vector. And what is this? This is x n C transpose. This will be D transpose, isn't it? If you take D as x n matrix into a C, and C is a non-zero vector. So, x n into C, if you call it D vector, if you take transpose of D, it will be C transpose x transpose A, that is what you have. So, D transpose, and D transpose D is norm square of D. So, norm square can never be negative. So, it is always non-negative. Okay, that is always true. But if it is not only greater than equal to 0, if it is strictly equal to 0, strictly greater than 0, then it is positive definite. Then we have seen in the very beginning of the lecture, positive definite matrices have positive eigenvalues and they are invertible. Now, when this equal to 0 occurs, equal to 0, it will be 0 if now what is this norm of D square? Norm of D square is D1 square, D2 square, D what? X n into C. Okay. So, it will be n cross 1 vector. X n is n cross p plus 1. You are multiplying by C. Okay. C is p plus 1 cross n. For any vector, let me write. So, p plus 1 entries in a vector C, you are multiplying by x n, there are p plus 1 columns. So, resulting vector will be length n vector, right. So, that is why. So, D is length n vector, norm square of D is this. If this is equal to 0, since every term is positive or 0, no term is negative, every term is either positive or 0. Positive or 0, and they are adding, there is no subtraction. So, they can only add, they can only contribute positively. So, the whole thing has to be 0, every term has to be 0, D1 square has to be 0, D2 square. It cannot happen that this is also positive, this is also positive, but there is a minus sign here, so they cancel. That is not there, it is all positive signs, additions only. So, if the sum total is 0 and every term is non-negative, there is either 0 or greater than 0, the only possibility is everybody is 0. right? Only then it is, so only if d vector is 0 vector, only if d vector is a 0 vector, then it will be equal to 0. It will be, therefore, but d equal to 0, what does it mean? D equal to 0 means xn into c 0. This c is 0. This c, c0, c1, let me write and xn. What does this matrix times column vector, what does it mean? It is basically linearly combining the columns, okay, by these coefficients. This actually c0 times xn vector, c1 times xn minus 1 vector, like that. So, c0 times xn vector, c1 times dot 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 cp times last guy. Okay, that is all 0. This means there is a linear relation amongst the columns. Suppose C0 is non-zero. Okay, so I keep this term C0 xn on the left hand side, take the others on the right hand side, C0 non-zero. So divide both sides by C0. That is possible because C0 is non-zero, I am assuming. So I will have xn, right hand side will be minus C1 by C0 xn minus 1, minus C2 by C0 xn minus 2, dot 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 minus Cp by C0 xn minus p. So xn will be a linear combination of xn minus 1 to xn minus p. That means there is some linear relation amongst the columns. We assume that no such linear relation exists. We assume no such, because it is all coming from random data. There is no model inside, so that the columns are always governed by an equation of that kind, okay, because the data is just randomly coming. All right, I am giving xn data random, purely random. I am not giving data where there is a hidden linear dependence relation like that amongst the data samples. So that the columns, they become linearly dependent. Okay. If that be, then obviously d cannot be 0, because the moment d is 0, it implies this, which means the columns are linearly dependent, that is, there is a linear relation between them. That is not, I mean, that is something we can always say it won't occur, because I am giving xn data randomly. There is no linear relation, hidden linear relation amongst the data. They are all coming independently, I mean, just random, purely randomly fluctuating. So you can never have these columns generated by the data as linear dependence. But this may not happen if this number of row, if number of row n becomes less than p plus 1. Okay. Then columns are linearly dependent. Okay, I will tell you why. Okay, that means there will be some linear relation between the columns, and there you can, by appropriately choosing C0, C1 to Cp, you can find, okay, a linear combination which is d, that is xn times c, d equal to 0 even if c is non-zero. Okay, because of this linear relation, that will always happen. Why? Because now every column vector is length capital N. Okay, so every column vector lies in a space of dimension capital N. So I can have maximum capital N number of axes, which are called bases vectors. Okay, in an n dimensional space. So if you have more columns than the number of axes, number of bases, like suppose this is one axis, this is one axis, these two are fine. You call it x axis, you call it y axis. But if you have another fellow here z in the same plane x, y, z, okay, that is dimension was 2. I have 2 vectors spanning this plane. There if I pack one more fellow z, then this set is linearly dependent, because z I can always write as something times x, something times y by the parallelogram law of vector addition. Similarly, every xn is length capital N. So, they are belonging to a space of capital N cross 1 vectors that has dimension capital N. So, it can have maximum capital N number of axes, that is basis. Any extra vector will be writable as a linear combination of this basis, that is of this axis, capital N number of axes. So, there will be a linear dependence relation in that case. Therefore, we should always avoid these, that is choose okay. Then we can always argue that the data which form these columns, is such, data is generated randomly from outside and there is no linear relation then, governing the data, so that there will be some linear relation between these columns and all that. That is a reasonable assumption. But if n is less than p plus 1, you cannot make that assumption, because then every column vector is an n dimensional space, but p total column vector is p plus 1, which is more than n. So, when if capital N number of x's, that is basis vectors, are taken out, okay, there are still extra vectors left. They can be written as a linear combination of those basis vectors, those axis vectors. Okay. So, this is important. So, now this is the equation, this is lambda. 1 minute. This is lambda. So, now I am assuming x transpose x n is indeed positive definite and therefore invertible. So, both left hand side and right hand side I multiply by the inverse of this. Okay. So, I get lambda vector to x transpose n, x transpose x inverse this inverse, then x transpose n w n minus w. Okay. So, this is lambda, and the constraint that we had x transpose n w was equal to d n. If I take all these partial derivatives and put in a stack, we have discussed this at length earlier, that this constraint will be satisfied, it will be x transpose n w equal to d n. So, I have got another thing, that is x transpose n into w equal to d n. All right. X transpose n w is d n. Then come to this equation, 2 w n minus w is x n lambda. Lambda I will put here, 2 w n minus w is x n lambda. Okay. So, lambda you put here. So, this 2 comes, x n, this x n, x transpose n xn inverse, then this x transpose n wn minus w. All right. So from here we will find out, we have to apply this constraint in this. I see the 2 cancels, 2 and 2 cancels, right. So x transpose n w equal dn. So x transpose n w will be dn. So what if you have that, you will have 2 has already cancelled. I take a minus negative of both sides. 2 and 2 cancelled and take negative of both sides. So, w minus wn. Remember, this w will be by w n plus 1. So, w minus wn is minus, and minus sign I will observe here. So, no need to write minus separately. Okay, 2 cancels. So, you have got x n now x transpose n w n, minus will come on that, and x transpose n w is this d n. So, it will be x transpose n w, because I have taken minus of both sides. So, that will be positive, this is negative. X transpose n w is d n. So, this is my d n vector minus x transpose n w n. All right. So, if then w will be what? There is w, that is that I will equate as w n plus 1. So, update equation will be this. I am taking to the right hand side, plus x n this vector d n is a vector, x transpose n w n, that is also a vector. This vector, let me give a name E n. So, this is my E n vector. Okay. Now, what is E n? Now, let us see, E n means d n minus this, right. So, d n was d n minus 1 dot d n minus p, and minus x transpose n was, this was x vector, then x n minus 1 vector, all these were done earlier, x transpose n minus p vector into w. This is my E. What does it mean? That w, instead of w, now it is w n. So, w n is the filter coefficient vector at the nth clock, right. Suppose I hold it. At nth clock, filter output will be x transpose n w n. I subtract d n, that from d n I get the output error. But now suppose I use the same filter coefficient, but take a look back. I say that suppose I go back, use these coefficients only, but use it in the previous clock n minus 1 n. That time my input data vector was x n minus 1. So, then filter output with these coefficients will be x transpose n minus 1 W n. So, that if I subtract from d n minus 1, that will be the next component of error. You understand that filter coefficient is not changing. At nth clock, whatever filter coefficient I have, suppose I am freezing and I am taking back, I am looking back, that suppose I now use these coefficients only, not W n minus 1, but this W n, but still at the previous clock, okay, at the previous clock. So, that time my filter input vector was x n minus 1. So, filter output would be x transpose n minus 1 and this filter W n, and that I subtract from d n minus 1. So, I get the corresponding error. And same, next is x transpose n minus 2. So, if I use the same filter coefficients, but at go back and to n minus 2th clock, then my filter input is x n minus 2 vector. So, x transpose n minus 2 W n. Okay, that is my filter output. That I get subtract from d n minus 2. Okay, and this, so it is, that is why it is called a posteriori error. That is, I have W n and now I am going back to previous clocks using that filter coefficient, recalculating the output error, okay, that vector. So, this is the APA, basic APA weight update formula. Some modifications will be done on this as before. So, that I will do in the next class. Thank you very much.